This is my solution to the quality control case. So the quality control case asks us to use regression analysis to help diagnose why some factory has far too many defects. So we have a dependent variable which is defects, and in working with the engineering staff, we've identified 4 possible causal factors. So the first is temperature variability, measured by the standard deviation during the the process. Okay, so remember, a standard deviation is 0 means there's no variation. So when temperature equals 0, the standard deviation of temperature more precisely, what that means is that the temperature is completely constant while we make whatever we make. Density refers to the density of the product. So, assuming all the products have the same volume, what density means is, how heavy is that product. Rate of production is just how fast we work. And then we have 2 shifts, a morning shift and an evening shift. The variable AM takes the value 1 for the morning shift and 0 for the evening. All right, so let's follow the instructions. We're going to generate a scatter plot matrix and a correlation matrix and interpret them. What obvious conclusions can we draw? So you have my R code, quality.R gives you all of this. You'll see I generated the scatter plot matrix and the correlation matrix. And the obvious conclusions are, here's the temperature axis versus defects. So defects versus temperature, I'll always list the dependent variable first. What we see is a positive association, very strong positive association, where the more temperature variability there is, the more defects we produce. This is the density axis up here. So what we see with density is that the higher the density, the lower the defect rate. So we like a nice dense product. When we look at rate of production, we see a strong positive association indicating the faster we work, the more defects that we make. And that doesn't surprise me. Whenever I work too fast, I make a lot of mistakes too. All right, when it comes to the 2 shifts, there's a pretty clear pattern here that it looks like the afternoon shift. So remember, when AM is 0, that's the afternoon shift versus the morning shift. It appears that there are fewer defects. Morning shift produce more defects. That's kind of corroborated by the correlation, which is positive 0.535, indicating as AM increases, as you go from the afternoon to the morning, defects also increase. Okay, so we've addressed the first question. Second question, perform a multiple regression predicting rate from all 4 variables. Is the overall model significant? Which predictors, if any, are significant? So let's go do that. So here's the regressing defect on everything else, and here's the output. So we were asked to test the overall significance. So the overall significance is going to be tested with this p-value. Now let me remind you what the null hypothesis is for this. So the null hypothesis is that all of the 4 slopes, so temperature, density, rate, and AM, are simultaneously equal to 0. So in other words, none of these predictors explain defects at all. The alternative is that at least one of these 4 slopes is non-zero. Now, the p-value is absolutely tiny. Okay, so what that means is we can reject the null hypothesis and conclude that at least one of these 4 variables is related to defects. So now we're asked which predictors, if any, are significant. And this is where there's a bit of a puzzle, because none of the predictors are significant. All of these p-values are greater than 5%. So we can't reject the null hypothesis that each one of these is equal to 0. So that's very much a paradox, because the overall test said that at least one of them is different. Now none of them are. The R squared is pretty large, yet none of the predictors are significant. So compute and interpret variance inflation factors, and what can we can we conclude from this? So here are the variance inflation factors, and remember, these variance inflation factors tell us how much larger the variances of our slopes are due to the correlations between the predictors, the multicollinearity. If we go back to our correlation matrix, there's a lot of multicollinearity here. So these correlations are all very large. And so these variance inflation factors are very large, 16, 18, 7.7. And what that's telling me is that the reason we can't reject any of these individual tests is because the standard errors, so the standard errors are just the square roots of the variances, are so inflated that these values are much larger, so the t-statistics cannot be large. If you stick a very large number in the denominator, none of these are large enough to be able to reject the null hypothesis that one of these slopes is equal to 0. All right, so let's move on. If we were to predict defect from each predictor separately, what you'd find is that each one on its own is highly significant. So more temperature variability, more defects. More density, less defects. Higher rate of production, more defects. And finally, if we look at the effect of shift, the morning shift is producing more defects on the average than the afternoon shift. All right, so would it be appropriate to use a stepwise regression? We haven't really talked about stepwise of principal components yet, so we're going to just disregard those for now. So the question is, what do we conclude here? And usually I have a fairly long discussion over this, but basically we have the wrong model. Okay, so remember I said, what do you do about multicollinearity? Well, the first thing you have to do is understand why you have multicollinearity. And in this case, the reason is probably that the predictors are causally related. Okay, so let's go over to, I did some sketches in PowerPoint. The model we've just estimated is described by this diagram. So all 4 of the predictors go into the model to predict defects, when in fact the real model looks something like this. Okay, so if I work very fast, I get more temperature variability when I'm making the parts. That temperature variability causes problems with density, and that's what's causing the defects. All right, so I'm estimating the wrong model because my predictor variables are correlated with each other. Now, of course, you might want to check with some engineer who really understands the process of whatever's being made, but this seems like a pretty reasonable explanation for why exactly these variables are correlated with each other. So as we work faster, we get more temperature variability, which produces issues with density. So that's not something that the regression model is going to tell you. You have to understand the situation. You have to think about which models you fit. The regression analysis will not just automatically tell you that. All right, so really the only decision variable in this problem is the rate of production, because the other 2 temperature and density variables are consequences of the rate of production. All right, well, let's go back to the case. To compare the 2 shifts, would it be appropriate to use an independent sample t-test? How is this different from multiple regression? So the independent sample t-test is equivalent to this last regression I ran. And in this last regression, we conclude that the morning shift has significantly more defects than the afternoon shift on the average. However, if we were to fit a regression that includes rate, we come to a very different conclusion about shift. Here, shift is not significant. So what this means is I don't have any evidence to say that the morning shift makes more defects than the afternoon shift because the p-value is nowhere near being significant. So then the question is, which model do we trust? And the answer is we're going to trust this model because rate is one of those omitted variables. If we were to leave it out, it would be an omitted variable. And so let's go back to the course packet and go back to my omitted variable bias, and you can see it again here. So in this case, beta 2 would be the effective rate, which is positive. The correlation between rate and shift was also positive. Okay, so what that means is if we were to estimate the model using only AM, so that'd be like an independent sample t-test, we would have an upward bias. We would overestimate the effect of the shift on defects. And sure enough, that's exactly what happened. Instead of having one more defect per 1,000, we estimate it at 20. And so that's the upward bias due to the omitted variables. All right, so in summary on this, you have to think about the domain, the situation that you're in. You can't just dump your data into a regression and expect it to sort out issues of what's causing what. So I like to summarize this as you have to think before you fit a regression model.